Alright, problem 31, we have a radical function that we have to graph. Let's just review really quick what a radical function looks like, because this would be the parent function of this right here. So let's look at some values really quick. Right away we should notice x, the lowest x can be a 0, and then you plug in a 1, you get 1, and 4 gives you 2. So 0, 0, 1, 1, 4 gives you 2. This is what this function looks like. Okay, and so this function is very, very similar to that thing, except this minus 3 takes the y value and always lowers it by 3. So the actual function here would just be starting at 3 lower and look something like that. Okay, you could generate a list of points for that, just like I did over here for the parent function, but it's easier to understand. I shift down by 3. So let me show you how I'd actually graph this thing. I would say, okay, I'm shifted down by 3. I know the parent function usually starts at 0, 0. This one starts 3 lower, but it counts just like the parent function from this starting point, 0, 0, over 1, up 1, right there, and then over 4, up 2, right there. And so you get the same graph that I showed you previously. Okay, problem, ooh, I'm going to have to copy this thing. Problem 32, very similar. The parent function for this one is also y equals square root of x. But notice the starting point. It's going to be shifted up by 1, and inside here it's going to be left by 3. Okay, remember it's always what zeroes that interior part of the function out. So I'm going to go left 3 and up 1. So this is my starting point. If this was a negative root x or a negative in front of that, it'd be upside down, but it's right side up, and so it follows that same pattern that we just saw, 0, 0, 1, 1, 4, 2. So I'm counting from my first red dot. That was my 0, 0. That is up 1 over 1, and then I'm going to go over 4 and up 2. Okay, so these values, these coordinates I gave you, are actually counting points for my function. However, the function actually contains the points negative 3, 1, this point looks like negative 2, 2, and this point looks like 1, 3. So those are the points of the actual function. I just used this parent function to graph it rather quickly. This next function is a inverse variation function, y equals 4 over x. This follows the model y equals k over x. We've talked a lot about these denominators. Denominators can never be 0, so x can't be 0. That means there's a vertical asymptote right there. Okay. The degree of the denominator is 1. It's actually the first power. So there's also a horizontal asymptote at y equals 0. So this thing has 2 asymptotes, one horizontal and one vertical. Then you could grab your calculator, or we can generate a few points for this thing. Okay, x and y. Again, you can't plug in 0. You can't do 4 divided by 0. So you can plug in something like 1, and it gives you 4. And you can plug in something like 2, and it gives you 2. And you can start to see a trend right away. 1 gives you 4 up here, and 2 gives you 2, and you're going towards these asymptotes, and hopefully things trigger at that point in your head. We haven't plugged in a fraction yet, like a half. If you plug in a half up here, you get, how many halves are in 4? You get 8. So at a half, it jumps way up here to 8, and you can start to see how the asymptote kind of fits in there, if I can get my 8 in there. And so this function rides right along like this. If you recall, these things had 2 branches. Notice I haven't plugged any negative numbers in yet. If I plug in negative 1, though, I get negative 4, and negative 2 gives me negative 2, and negative a half gives me negative 8. So it does the same thing over here. And I'm not going to graph it as specific, it's kind of difficult to do. There we go. There's the 2 branches, and they both approach the asymptotes that we had predicted. Alright, 34, we're on to logarithms. Okay. It's just a pattern. Remember, logarithms, you use the base of the exponential function. So this is a log base 3 of 9, and the logarithm tells you the exponent. So log base 3 of 9 equals 2. Evaluate these. Now to evaluate a logarithm, we actually convert to exponential form. This is saying my base is 6 of the logarithm. It's asking what's the exponent that gives you 36. And the answer to that is it must be a 2. The next logarithm says, hey, my base of 3 to what power gives me 1 over 27. This one's not as easy to do just by looking at it. So I'm going to create a little space up here. So what we do is we try to get common bases. 27 can be written as a 3 cubed. Negative exponents allow me to write that as 3 to the negative 3, the reciprocal. And now that the bases are identical, the exponents must be the same. So the exponent of negative 3 must give me 1/27th. So log base 3 of 1/27th is negative 3. Finally, on this little logarithm section, we have the natural log of e equals 4. Natural log is a logarithm base e. So this equation could have been written this way, or this question could have log base e of e to the 4th power. So exponential form again just says your base e to what power gives you e to the 4th. And the answer is fairly clear. It's just 4. And we had that actually as a rule that we learned. 39, right, is a single logarithm. We had several rules for that. This one uses the power rule, the coefficient rule, that says if you have a coefficient of a logarithm, it can move up to an exponent spot. So this first log becomes log x to the 4th minus log x to the 2nd. Then another rule said that if you have subtraction of two logarithms, you can write that as a single log of a division problem, x to the 4th over x squared. Notice it's not two logarithms anymore, it condenses down to one, and that simplifies. You just log x squared. You got 4 x's on top here and 2 on the bottom, so they cancel 2, and you're just left with the x squared. It's actually the subtraction property or quotient property for exponents. Expand a logarithm, you're using the laws of logs again, but you're going in reverse. Now you're going to blow this thing up into several logarithms. So we have multiplication. We change that into addition. And then we have an exponent that's going to pop out front as now a coefficient. So there, that logarithm is expanded. And use your calculator to evaluate this one right here. On your calculator, our calculators do base 10, although some of yours you can change the base to base 4. I'll do it like we don't have a calculator that does it, and so you'd just type in log base 28. Now it's base 10 divided by log base 10 of 4. So if you type that into your calculator, it'll give you the correct answer. This question is actually asking 4 to what power gives you 28. 4 to the 2nd power is 16, and 4 to the 3rd is 64. So, I don't know, 2 point something. I'm not sure exactly. I don't have a calculator in my hands right now to do it.